Okay, so now you prepared quite carefully for going into the real utility maximization problem solving. So let's do it here with the Lagrangian setup that we have seen last week. And what does it have to do with the first order condition that we just explained in the last part? So let's do it. So again, here we want to maximize a utility function of two goods, depends on two goods, x1 and x2. Now, with respect to x1 and x2, we want to solve for these two variables at that optimizing point, subject to a constraint which is income equals p1 times x1 plus p2 times x2. Let's write the constraint a bit different. So we could write I minus p1 x1 minus p2 x2 equal 0, right? Alright, let's go with the Lagrangian setup. So we write the Lagrange function means doesn't look nice. The Lagrange function or setup is we have L is a function of x1, x2, but now also a new variable like the lambda for the constraint, right? We said that equals u, the utility function itself, plus lambda, that's where we need the lambda, of the constraint, times the constraint, px1 minus p2x2, that's the Lagrange function. So now we will set up the first order condition of the maximizing using purely mathematical tools that we learned last week. So the first order condition is the derivative of L, the Lagrange function, with respect to x1, which is, in this case, there's two separate functions. So the derivative of it is the sum of the derivatives of the two separate functions here. So that means we take the first derivative of the u with respect to x1, right? Plus, okay, so here, there you don't have any x2, so it's constant times lambda, now treated as constant because we only care about the partial derivative of L with respect to x1. So lambda times p2x2 is the whole constant, taking derivative is e, 0, one thing, gone. So lambda times I, here also constant, right? So another thing's gone. So the only thing we will have here at the end is lambda minus lambda, times p1 x1. That's the only thing left when we factor out everything. So the derivative of this term with respect to x1 is, now it's not minus, but it's not plus, but it's minus instead. So minus lambda p1, right? Let's denote this 1. second thing, which is saying that the derivative, the partial derivative of L with respect to x2 equals similar, very similar derivative of u, utility function with respect to, and it's a d here, x1, right? Whatever u is, we don't have to care this thing. Then, similar to this, but now p1 x1 is gone. We have p2 minus p2 x2 times lambda left. So that should be lambda times p2. Oops. I missed something here, very important. So don't make similar mistake. Equals 0. Set the first order derivative equals 0, right? Yep. Then the third condition is the partial derivative of L with respect to lambda. Will be, what is the derivative of the Lagrange function with respect to lambda? There's no lambda in the utility function, so it's gone after taking derivative. So now, like the second term, the second part of the Lagrange functions, if you take the derivative of this part with respect to lambda and everything else is constant, then you get the budget constraint again, right? P2x2 equals 0. This is the third first order condition. And this is saying exactly the same thing that we have on the budget constraint. Remember that? So now, look at the first condition equation, the first one. So du over the x1 again is the marginal utility of x1, right? Equals lambda p1. And then the second equation say that the marginal utility of x2 equals lambda p2, right? Now, what if we divided the first, I will call it one start equation and two start equation. So what if we divided one start and two start? What do we get? Two start equals, on the left hand side we have mu x1 over mu x2, right? What is that? Which is exactly the marginal rate of substitution of x1 for x2. We have seen, right? Equals, now comes to the right hand side. So you have lambda divided by lambda, simplifies gone, and at the end you have p1 over p2 is similar to what we've seen before. It is, right? So that is actually the minus of the slope, or the negative of the slope of the budget constraint. And here again, It is the minus or the negative slope of the indifferent curve. Which is exactly the first order condition that we have seen based on the graph that we have talked so far. So that's why Lagrange approach, the Lagrangian approach, is a very nice and elegant way to solve for the utility maximization given budget constraint that we're interested in now. And that's why we could use it. So keep in mind the idea behind. And for now, you don't have to look at the graph anymore. And then we can just go with the Lagrangian approach. Okay, how do we solve this maximization problem with the Cobb-Douglas CD? Cobb-Douglas utility function. Let's see. The first thing, we have to set up the Lagrangian function, right? So L, function of x1, x2, and lambda equals u, the function u, in this case is x1 to the power of a times x2 to the power of 1 minus a plus lambda times the constraint. So I minus P1 x1 minus P2 x2, right? First order condition. How do we solve it? Take it slowly. So the first one would be the partial derivative of L with respect to x1, right? Equals now the derivative of this part first. So exponent goes first. Again, well, actually we could just take the result that we derived last time with the slope, but okay. So x2 1 minus a remains plus, not plus again, sorry, minus lambda times P1 equal 0. And here we can already rearrange it a bit, equivalent to a time, x1 to the power of a minus 1, right? A minus 1 times x2 to the power of 1 minus a equals lambda P1. Let's call it equation 1. Second condition, first order condition, which is the partial derivative of L with respect to x2 equal now 1 minus a times x1 to the power of a remains x2 to the power of minus a. If you remember, then lambda px2 minus lambda px2 equals 0, and rearrange it in a way that we have 1 minus a times x1a to the power of a times x2 to the power of minus a equals lambda times p2, and this is the second equation. The last one is the partial derivative of L with respect to lambda, which is again the budget constraint. Minus p2 x2 equals 0. And this is the third one. How do we solve that? So the idea of solving these equations, we have 3 variables and we have 3 equations, should be solvable. So solving it means we will simplify it, we will rearrange it, so that at the end we get a result, the optimum number of x1 and x2. Here I missed the subscript 1, which is functions of only the constant parameter, the parameter, not other variables. So let's do it. So here again, when you divide 1 over 2, you would have a over 1 minus a times, we did it already, so here I will just skip the detailed, x2, right, over x1, now, equal p1 over p2. And that means we could actually write x1 or x2 as a function of all the others, especially the remaining variables. So we could write it as, for example, x1 equals a over 1 minus a remains on this side times x2 times p2 over p1, right? Okay, so you multiplied all sides by 1, but by x1, and then divided it by p1 over p2. So let's call it the 4 equations. Now you have a function x1 of x2. You can substitute it to the third equation over here to solve for x2. So let's do it. Substitute 4 into 3. We have I minus p1 times x1. Watch out, x1 is now this guy, right? So let's write it. p1 times a over 1 minus a times x2 times p2 over p1 minus p2 x2, which equals 0. Now let's simplify it. For solving, you have to simplify now. This is already different from before. So here you have 1p1 on the numerator and 1 in the denominator. So they cancel out. So that, and then that means you have I minus a over 1 minus a times p2x2 minus p2x2 equal 0. Now you can factor out the p2x2. So here we would have I equals a over 1 minus a plus 1, right? You factor p2 x2 out because they're same here, and that's why. That means I equals, now let's simplify this term by multiplied it with 1 minus 8, both on the numerator and denominator of 1. So we would have a plus 1 minus a over 1 minus a, right? Times P2 x2. And here you could simplify the two a's already. It will be 1 over 1 minus a over here. But now let's solve for x2 start, which is the optimal consumption of x2. We can already go here. So I, on the numerator here you have a, and here in the denominator minus 1 minus 8. So you will multiply both sides by the inverse of it, right? But before that, divided P2, then times the inverse of it. So A over 1, right? That means your demand function of x2, here we denote x2 star, which is I over P2 times one minus a. Sorry, I messed it up. So here it should be 1 minus a, not a, but 1 minus a. So this is the demand function. The solution for the optimum level of consumption of goods. At the end, we saw from a utility maximization, it's called the Marshallian demand function of the goods, here x2. Let's try to solve for x1 start from here. Nah? So you substitute x2 here with x2 start, the result that we just arrived. And then you would have, I write a different color so that it's not confusing. Substitute, not substitute, but plug in x2 start. We would have x1 start equals, let's make some space, my favorite way. So x1 start equals a over 1 minus a times P2 over P1, rewrite it. Now x2 start, I over, right, P2 times 1 minus a, and then simplify it. 1 minus a is gone. P2 is gone. So at the end we have, we write it here at 1 start equals a over P1 times I. And this is the demand function, the Marshallian demand function of x1. given the utility maximization problem and our budget constraint.